Hey guys, here's the review for your senior final. First off, I'm going to start with graphing some exponential functions, and to do this, we're going to start by identifying my asymptote. In this case, it's going to be at -1. Alright, so it's right here. I'm going to label that as -1. And I'm going to use the strategy we've been using for graphing logs, which is to identify points that make my exponent -1, 0, and 1, just to make our lives a little bit easier in terms of graphing. To make the exponent -1, we're going to use -2. To make the exponent 0, we're going to use -1. And to make the exponent 1, we're going to use 0. When I plug in -2, we get 4 times a half, which is 2, minus 1, which is 1. When I plug in -1, we get 4 times 1 is 4, minus 1 is 3. And when I plug in 0, we get 4 times 2 is 8, minus 1 is 7. Let's plug those 3 points in, so -2 and 1, -1 and 3, and 0 and 7. And draw a nice sketch of our graph going through those points and approaching that asymptote. The domain for this graph and for all exponential functions is all real numbers. And the range for this graph is going to be anything that y is greater than -1, because that's where my asymptote is, and this is above that. Next, we're going to look at number 5, and for number 5, we've got an exponential equation. Our goal is going to be to make this all the same base. 81 becomes 3 to the 4th, and that's the 2k. 3 to the 3rd is all set, and we get 3 squared to the 2k. If I'm dividing, that means I'm going to subtract my exponents on the left side, so we get 4 times 2k is 8k minus 3, and on the right side we're just going to multiply those two to get 4k. In solving this, I'm going to have 4k on the left and 3 on the right, so k is equal to 3/4. For number 9, we've got to evaluate the log expression, and for this we're looking at log base 4 of 64. I'm probably going to rewrite this as an exponential, and so I've got 4 to some exponent is equal to 64. Since 4 to the 3rd is 64, log base 4 of 64 is equal to 3. 3 is our final answer. For number 17, I've got to rewrite this in exponential form. So we're looking at 18 to the power of -14 is equal to a. Similarly, for number 21, I've got to write this in logarithmic form. That's going to be log base 15 of 1 over 225 is equal to -2. For number 26, I've got to expand this. First thing I'll do is to break this apart, since we're multiplying on the inside. It's going to be by adding. So log base 4 of y plus log base 4 of z plus log base 4 of w. I know a cube root is the same as a 1/3 power, so I'm going to rewrite this as log base 4 of x to the 1/3. Only thing I have to do is bring that 1/3 down front. So we get log base 4y plus log base 4z plus log base 4 of w plus 1/3 log base 4 of x. For number 30, we've got to go the opposite direction and do some condensing. I'm going to set this up with my log at base 5, nice big parentheses with a fraction bar in the middle. Positive things are going up top, so we've got x to the power of 2, so x squared. Nothing else is positive. Negative things go on the bottom. That's going to be a z and a y to the power of 2. And at that point, you're done. Moving on to solving some equations. There we have a few different types of equations you have to know how to solve. The first type is going to be an exponential that can't be solved without logs. So I might start by adding 2 to both sides and dividing by 6 to get the exponential expression by itself. 16 to the 7v plus 1 is equal to 2 over 6. Next, I'm going to take the log of both sides. In other words, convert this to log base 16 of 2/6 is equal to 7v plus 1. Minus 1 to both sides and divide by 7. I get log base 16 of 2/6 minus 1 over 7 is equal to v. For number 38, I see that I've got a log on both sides that has the same base, and there's nothing else in this problem. When this happens, what I can do is say that, okay, we've got log of something equals the same log of something. That means the insides have to be equal. So negative 5p minus 10, that's at p, there we go, that's a 10, is equal to 8 minus 4p. I'm going to add 5p to both sides, and I'm going to subtract 8 from both sides, and I get that p is equal to negative 18. For number 41, here we've got a log expression that's just a single log expression, and a whole bunch of other numbers. I'm going to treat this a lot like I treated the exponential equation that I had to use log to solve, and just try to get this piece by itself first. So I might subtract 10 from both sides and then divide by negative 3. So I get log of base 4, negative 9v minus 3 is equal to, that was 13 minus 10 is 3 divided by negative 3, negative 1. I'm going to convert this to an exponential function. So 4 to the negative 1 is equal to negative 9v minus 3. That means 1/4 plus 3 would be 3.25 is equal to negative 9v. That means that v is equal to 3.25 divided by negative 9. Or I can think about that in terms of 13 over 4, which is the 3.25, divided by negative 9. Which is the same as negative 13 over 36. For number 46, we've got two logs going on here and a number. I might notice that, I really wish to put parentheses around that. We've got a subtraction between them. I can condense these, and if I'm subtracting, that means I'm going to divide my logs. So we get log base 9 of negative x divided by 6 is equal to 1. At this point, I'm going to convert this to an exponential. So 9 to the 1, or just 9, is equal to negative x over 6. I'm going to multiply both sides by 6, and I get negative 54. 54, I'm going to make that negative to get rid of that in a minute. 54 is equal to negative x. That means that positive x is equal to negative 54. Graphing a log graph, the first thing I want to do is to convert this to an exponential form to make my calculations a little bit easier. And I'm going to do the same thing I started to try to convert us towards at the end of this unit, which is keep my x and y as is instead of actually finding the inverse. So I end up with y plus 3 is equal to log base 3 of x minus 1. Converting that to exponential, 3 to the y plus 3 is equal to x minus 1. And then x is equal to 3 to the y plus 3 minus 1. All right. First thing from this, we can get our asymptote. I can either look here and see that x equals 1, or I can realize that my asymptote here is going to be 1 also. All right, so we can get a vertical line in. I'm going to make a yx table. Remember, I'm going to have to graph this backwards. And a nice way to do this is to try to make my exponent values negative 1, 0, and 1. Okay, to make this negative 1, that's got to be negative 4. To make this 0, that's got to be negative 3. And to make this 1, that's got to be negative 2. Plugging those in. 3 to the negative 1 is a third, minus 1 is negative 2/3. So at negative 4, we're going to be at negative 2/3. But now I'm thinking in terms of x and y values. I need to get that out of my head and switch that around so that negative 2/3 should give me a value of 4, which seems kind of suspect. I'm going to hold on to that thought for a minute. That seems kind of suspect to me because we shouldn't have anything over here. And in fact, when I solved this equation, instead of adding 1 to both sides, I just subtracted 1, which was not okay. That should be a plus. So instead of negative 2/3, I'm going to have 1/3 plus 1, which is 4/3. And that gives us an x value that is somewhere right in this vicinity. That's a lot better. I want to be to the right of my graph. We don't have a negative x in there. Okay, next point. 3 to the 0 is 1, plus 1 is 2. So that means x is 2, y is negative 3. So 2, negative 3. And then we're going to plug in the next one, so we get 1 in the exponent. 3 to the 1 plus 1 is going to be 4. 4, negative 2. And now we can see our quintessential log curve come out of that. What a beautiful curve that is. And finally, we might think about the domain and range. The domain here, I start at an x value of 1, and I go to the right, so x is greater than 1. And the range for all log functions is all real numbers. I don't know why I put an all real numbers thing instead of range. And now I'm in matrix land. I'm going to take a look at problem 56. You can see there are already a bunch of problems done out. But 56 is where I'm going to dive in. Okay. So see there are two things going on here. I've got stuff in parentheses, that's over here. And then I've got something that I'm going to subtract that from afterwards. The first thing I noticed is that in parentheses I've got to do some multiplication. So that's going to be row 1, column 1 first. I'm going to rewrite this guy down here. Negative 1, negative 2, 3, 6, negative 5, negative 1. And then I'm going to build my matrix here. So row 1, column 1, negative 2 times negative 1 is 2. Negative 4 times 3 is negative 12. 2 plus negative 12 is going to be negative 10. Okay, then I'm going to do, let's change colors slightly, row 1, column 2. And for that, I'm going to have negative 2 times negative 1 is negative 2. Negative 4 times negative 6 is positive 24. Negative 2 plus positive 24 is going to be 22. Okay, let's switch over to some greens for the next row. Row 2, column 1, that's going to come in here. I know I'm going to have a third row, so I'm going to try to keep this neat here. Negative 3 times negative 1 is 3. 6 times 3 is 18. We get 21. Doing the same thing. Row 2 times column 2. Negative, I'm going to label that. Negative 3 times 1 is negative 3. 6 times negative 6 is going to be negative 36. We end up with negative 39. Okay, I'm going to switch colors a third time. Let's go with some oranges. We get row 3. It's going to be down here. Column 1. 4 times negative 1 is going to be negative 4. 1 times 3 is 3. That's going to be negative 1. Okay. And then for the last time we get, it looks like the same color. It wasn't meant to be. That's okay. 4 times 1 is going to be 4, and 1 times negative 6 is negative 6. This is row 3, column 2. And when I do that out, we get 4 plus negative 6 is going to be negative 2. Now it's a different color. That's fun. Okay, these are both still 3 by 2 matrices, 3 rows, 2 columns, which means that I can keep going. I can subtract these by subtracting the elements in the same position. Negative 1 minus negative 10 is going to be positive 9. negative 2 minus 22 is going to be negative 24. 3 minus 21 is going to be negative 18. 6 minus negative 39 is going to be positive 45. Negative 5 minus negative 1 is going to be negative 4. And then finally, negative 1 minus negative 2 is going to be positive 1. My final answer is this lovely matrix to the right. Alright, the other one on this page I wanted to talk about was number 62. Here we've got a matrix equation, and we're looking at trying to get A by itself, and remember that A is a matrix. So first thing we do is get rid of this guy, and to that I'm going to subtract that matrix from both sides. So we get 3A, and it's really plus 0, but we don't need to write that. 27 minus negative 6 is going to be 33. And negative 19 minus negative 7, that's going to be negative 12. Okay, now I'm going to multiply both sides by 1/3 to get rid of that 3. And we end up with A is equal to 11, negative 4 as a 1 by 2 matrix. Next up, I'm going to look at problem number 65. I'm going to do 2 of these out because we haven't seen these for very long. The big idea here is I want to get A by itself, and to do that I've got to multiply both sides by something to get rid of this matrix. The way we're going to do that is to multiply by the inverse of this matrix on the left side of both sides of my equation. So I've got to find the inverse of that matrix first. So let's talk about finding the inverse. So finding the inverse of this, we know we need to do 1 over the determinant. The determinant is going to be 2 times 0 minus 2 times negative 4. 0 minus negative 8 is 1 over the determinant, 1 over 8. And then I've got to consider the other pieces of this. I'm going to switch my A and my D term. That's going to become 0 and 2 instead of 2 and 0. And my B and C terms, I'm going to make negative. So negative 2, negative 4 is positive 4. This is my inverse matrix. This is what I'm going to multiply both sides by. And in this case, I'm actually going to multiply it out on the right side just to show us what happens to make sure that we're doing okay. I also like the strategy of keeping that 1/8 out front so we don't deal with fractions while we're multiplying. So I'm going to rewrite this as 1/8, and this is going to take a lot of writing, so bear with me for a minute. 0, 4, negative 2, 2, left multiplied by 26, 10, 14, 22. And I'm going to multiply this out now, just again holding off on the right side just so we can see why this actually works. So we've got first row, first column, and 0 times 26 plus 4 times 14 is going to be 56. First row, second column, 0 times 10 plus 4 times 22 is going to be 88. We're going to do second row, first column, negative 2 times 26 is negative 52. 2 times 14 is 28. Negative 52 plus 28, I really didn't want to do that in my head. I'm going to go with 24 and the negative variety. Oof. I'm like doing some addition in the morning. Negative 2 times 10 is negative 20. 2 times 22 is going to be 44. When I add those, I get 24. And again, I like keeping that 1/8 out front because now I can see that we've got 1/8 times all these things. Thankfully, they all come out kind of nice. 7, 11, negative 3, and 3. That's going to be our final answer here, but I want to see why that's our final answer. So for that, we're going to look at the right side of our problem. And again, I'm going to multiply that inverse matrix to both sides. So I'm going to rewrite that here. 2, negative 4, 2, 0, and then A. And I'm going to repeat the process we just did. First row, first column, 0 times 2 is 0, 4 times 2 is 8. That means we get an 8. First row, second column, we're going to have 0 times negative 4 is 0, 4 times 0 is 0. Okay. Second row, first column, we're going to have negative 2 times 2 is negative 4. 2 times 2 is 4. I'm going to add those, I get 0 again. And then finally, we're going to have negative 2 times negative 4, and that's going to be 8. And then we're going to have 2 and 0, so when I add to that, I get 8. Okay. And that's going to be multiplied by matrix A. So we're looking at having 1, 0, 0, 1, which we know is the identity matrix, multiplied by A. This is important because the identity matrix times any matrix of that size, or of a multipliable size, gives you that matrix out again. So we really have A is equal to 7, 11, negative 3, 3. I'm also going to do number 70, just kind of arbitrarily. And again, we're trying to get matrix Z by itself. And to do that, we have to do some kind of multiplication to get rid of this matrix, and we're going to multiply by that inverse. I'm going to find that inverse first. We know we're going to build it as 1 over the determinant. So it's going to be negative 14 minus negative 15, which happens to be 1. That's kind of nice. And then we're going to play around with this matrix. My A and my D terms are going to switch. So that's going to become 2 and negative 7, respectively. And then my B and my C terms, or I should have said C and B, are both going to switch their sign. So we get 5 and negative 3 instead. I'm going to write out the multiplication step. So we have 2, negative 3, 5, negative 7, multiplied by negative 7 and 3, negative 5 and 2, times whatever Z is equal to, and again the inverse, 2, negative 3, 5, negative 7, multiplied by negative 16 and negative 11. Okay, I'd like to remind us that we multiply a matrix and its inverse. The answer is going to be the identity. If you want to make sure that you did your inverse correctly, this is a great way to do that. If you don't get your identity, either you multiplied wrong or you built your inverse wrong. And then on the right side, 2 times 16 is 32. To that, we're going to add 33, that's 2 times negative 16, so negative 32 plus 33 is going to be 1. And then second row, I only have one column. 5 times negative 16, that's going to be negative 80, I think. That sounds right. And then it looks like we're going to add 77 to that. Negative 80 plus 77 is going to be negative 3. And we have our matrix. Oh, what the heck, I guess I'll do one more. Looking at 71, we're going to do the same thing. I'm trying to get B by itself, so I want the inverse of this guy, which is multiplied there. And that's going to be the determinant, 0 minus 6. So we're going to look at 1 over the determinant, 1 over 6. And then for the matrix, we're going to flip our A and D. 0, 1, and make our other guys negative. So it's going to become 2 and 3. Rewriting, so you get 1/6, 0, 3, 2, 1, 1, negative 3, negative 2, 0. B is equal to, I have to do this on the left side, 1/6, 0, 3, 2, 1. And then we're going to have negative 24, 2, negative 12, and 14. Okay, the left side again, if you multiply a matrix and its inverse, you should get 1, 0, 0, 1, the identity matrix, which when multiplied by matrix B should give you B as a result. On the right side, we have to do this multiplication out. Again, I like keeping this fraction out front so I don't have to deal with fractions in the multiplication part. I can deal with that after. 0 times negative 24 is 0, plus 3 times negative 12 is going to be negative 36. 1/6, negative 36, 0 times 2, 0, 3 times 14 is going to be 52. Is that 52? No, it's 42. 52 is 13 times 4. We're going to have 2, 1 multiplied by negative 24, negative 12. And that's going to be negative 36 also. And then finally, 2, 1 times 2, 14. 4 plus 14 is going to be 18. When I multiply all those by a sixth, I get negative 6, 7, negative 6, and 3.